565 meters. That is not the height of a skyscraper. That is not the altitude of a mountain peak. That is the distance between a road and the river running beneath it. An empty, vertical column of air, so deep that the river below looks like a silver thread. And someone looked at this canyon, this gash in the earth, and decided to drive a highway across it. Welcome back to the channel. Today, we are standing at the edge of one of the most extraordinary feats of engineering ever attempted by human hands. This is the Duge Beipanjiang Bridge, located on the border of Guizhou and Yunnan provinces in southwestern China, and it is officially the highest bridge on the surface of this planet. This is not just a bridge, it is not just a crossing, it is a cable-stayed structure hanging 565.4 meters above the Beipan River, stretching 1341 meters from one cliff face to the other, carrying a 4-lane expressway across a canyon so hostile, so remote, so geologically violent, that for most of human history, the people on either side of it lived in almost complete eternization. Think about what that means. 2 communities, 2 provinces, separated not by politics, not by language, not by choice, but by a single crack in the ground. A canyon so wide and so deep that before this bridge existed, the journey between Liapanshui and Zhuanwei, 2 cities that are practically neighbors on a map, took approximately 5 hours by road. 5 hours of winding mountain passes, crumbling switchbacks, and sheer drops. 5 hours because the canyon simply refused to be crossed. And then the engineers arrived. Before we go any further, if you find yourself leaning forward right now, that feeling is exactly why this channel exists, and stay with us until the end. Because what the bridge hides inside its structure, what most people driving across it will never see or feel, is the most remarkable part of the entire story. At first, there was only the canyon. No road, no tower, no cable, no foundation, just vertical limestone walls dropping into shadow, a river grinding through rock at the bottom, and wind that moved through the gorge like it owned everything inside it. The Beipan River had been cutting this canyon for millions of years. It had no interest in being cooperative. The walls on either side were not gentle slopes. They were near vertical faces of fractured rock, unstable in places, soaked by seasonal rains, cracked by earthquakes, and shrouded for much of the year in dense fog that rolled in from the valleys without warning. This was not a place that invited construction. This was a place that resisted it. If you tried to build a conventional bridge here, the kind that rises from piers planted in the riverbed, you would immediately face an impossible problem. The river is 565 meters below the deck level. Building piers from the river floor up to that height would require structures taller than any bridge pier ever constructed in history. The logistics alone would be almost incomprehensible. You cannot crane materials down a vertical cliff face. You cannot pour concrete from a platform that does not exist yet. You cannot stabilize a foundation in a river that floods violently during monsoon season. If you try to build from the bottom up, the canyon defeats you. And if you try to build from the top down, if you try to assemble the deck and lower it into position, you face the same problem in reverse. The spans are too long. The weight is too great. The wind loading in a canyon of this depth is not predictable. A suspended deck, swinging freely across 720 meters of open air in a gorge where the wind accelerates unpredictably, is not a structure. It is a catastrophe waiting to happen. So the solution was not a conventional bridge. It was not a suspension bridge in the classical sense. The solution was a cable, stayed bridge, a system of extraordinary elegance and extraordinary complexity, where the deck is not supported from below and not hung from a single main cable above, but is instead pulled upward and outward from multiple directions simultaneously by hundreds of individual steel cables, each one anchored to a tower of concrete and steel that rises from the canyon rim itself. The towers do not sit in the river, they sit on the cliff tops. They reach upward into the sky from solid ground. And from those towers, the cables fan outward and downward, each one gripping the deck at a precise angle, each one carrying a precise share of the load, working together. Without that system, there is no bridge. Without the towers, the cables are useless. Without the cables, the deck is weightless in the wrong direction. The tower needs the cable needs the deck. The deck needs the anchor. Every element in this structure is completely dependent on every other element, and building it in this canyon, in this terrain, in these conditions, took 3 years, from 2013 to 2016. The first task was the most fundamental. before a single piece of steel could be placed, before a single bag of concrete could be mixed, before a single worker could safely approach the canyon rim, the engineers needed to understand what they were working with. And the Beipan River Gorge did not give up its secrets easily. Survey teams descended into the canyon and climbed the cliff faces. They drilled core samples from the limestone to understand its strength, its fracture patterns, its behavior under load. They mapped the seismic activity of the region because this part of southwestern China sits on active geological fault lines. They measured the wind, not just the average wind speed, but the gusts, the turbulence, the direction changes, the way the canyon walls channeled and amplified airflow from the surrounding valleys. They studied the fog patterns, the rain totals, the seasonal flooding. Every wind reading mattered. Because in a structure of this scale, in a location of this hostility, a single wrong assumption in the data does not cause a problem. It causes a catastrophe. Then came the access problem. Before you can build a bridge over a canyon, you have to be able to get to both sides of it. In a normal construction environment, you simply drive your equipment to the site. In the Beipan River Gorge, there were no roads capable of carrying heavy construction machinery. There were mountain tracks, barely wide enough for a single vehicle, clinging to slopes that dropped hundreds of meters into nothing. The construction teams had to build their access before they could begin building their bridge. New roads were cut into the mountainsides. Tunnels were drilled through rock to create stable approach routes. Temporary facilities were established on both rims of the canyon, on the Guizhou side and the Yunnan side. Because the two teams working on opposite towers could not easily communicate across the gorge, they were for much of the construction period two separate operations working toward the same point in the sky. Then came the foundations. The towers of the Duge Beipanjiang Bridge do not sit on the surface of the canyon rim. They go into it, deep into it. The foundation pits were excavated through the surface rock and into stable bedrock beneath, creating anchor points capable of bearing not just the weight of the towers above them, but the enormous tensile forces pulling downward and outward through the cables. Imagine the force of a cable supporting a section of deck, a section weighing thousands of tons, hanging in open air, swinging gently in the wind. Now imagine hundreds of those cables, all transferring their load into two foundations, one on each side of a canyon. The foundations had to be engineered, not just for static load, but for dynamic load, for wind, for traffic, for seismic movement, for the slow creep of the ground itself. Over decades, the concrete was poured in stages, carefully, in controlled pours that allowed each layer to cure before the next was added, because concrete poured too quickly, in too great a volume, generates its own heat as it cures, and if that heat differential becomes too extreme, the concrete cracks from the inside. In a canyon where air temperatures fluctuate significantly between night and day, between seasons, managing the thermal behavior of the concrete was its own engineering challenge. Temperature sensors were embedded in the pores. Cooling pipes were run through the mass concrete to draw off excess heat. The two main pylons of the Duge Beipanjiang Bridge rise approximately 269 meters above their foundations. To put that in perspective, that is roughly the height of an 80-story building, constructed on the edge of a cliff, in an area with active seismicity, in weather conditions that included fog, rain, and wind that could stop crane operations. The towers were built using slip-form construction, a technique where the concrete formwork moves continuously upward as the concrete below it cures, creating a seamless vertical structure without construction joints that could become points of weakness. Workers lived and worked at elevation, where extended periods, rising with the towers as they grew. Every curve, every taper, every dimension of the pylon cross-section was determined by structural analysis. The towers had to resist lateral wind loads that increased dramatically with height. They had to carry the compression forces of the cables bearing down on them. They had to be stiff enough to prevent excessive oscillation in wind. They had to be tall enough to give the cables an efficient angle of attack on the deck, but not so tall that they became aerodynamically unstable at their tips. Every meter of tower height mattered. Every change in wall thickness as the towers tapered upward was calculated. Every placement of internal stiffening ribs inside the hollow concrete shells was engineered to a purpose. While the towers were rising on both sides of the canyon, the cable systems were being prepared. The cables of a cable, stayed bridge, are not single wires. Each cable is a bundle of individual high-strength, steel strands, wires twisted together into strands. Strands bundled together into a cable outer jacket and tensioned to a precise and carefully calculated load. The cables of the Duge Bridge fan outward from the tops of the towers in a pattern designed to distribute load evenly along the deck. Some cables reach nearly horizontally to anchorages close to the towers. Others sweep at steep angles to anchor points far along the deck. Together, they form a web of steel stretched across the open air, above the canyon. Installing those cables across a 720-meter main span, above a gorge 565 meters deep, was one of the most technically demanding operations of the entire project. You cannot simply stretch a cable across open air and pull it tight. The process begins with a pilot line, a thin, lightweight rope fired across the gap, using a specially designed launcher. Some pylons, that pilot line is then used to pull a slightly heavier line, which pulls a heavier one still, in a sequential process of increasing weight and strength until finally, a cable pulling line of sufficient capacity is in place to drag the first full steel cable across the gap. Each cable had to be installed because the tension in each cable affects the position of the deck, and the position of the deck affects the geometry of every other cable. The entire tensioning process was a simultaneous balancing act across dozens of cables on both sides. Of both towers, computer models had predicted the final geometry of the bridge. The construction crews had to achieve that geometry to within millimeters by adjusting cable tensions in a sequence developed and monitored by the structural engineers. Then came the deck, the roadway of the Duge Beipanjiang Bridge, the surface on which vehicles traveled, the platform. These sections were manufactured off-site, transported to the canyon rim by road, and then lifted into position by tower cranes and cable-hung platforms. Each section was lifted, positioned, connected to the cables above and the previously installed deck sections on either side, and then welded into place. The welds were inspected, the geometry was checked, and then the next section was lifted. Imagine standing on a partially completed deck, 500 meters above a river, welding steel in a fog that reduces visibility to 20 meters, while a crane above you holds a 200-ton steel box in position, and the wind moves the entire structure deck, cables, towers, in a slow, barely perceptible sway that you can feel through your boots, but not quite see. That was the working environment for the teams who built this deck. Every weld mattered, every bolt mattered, every measurement mattered. The deck sections were not simply flat platforms. Each one contained within it a complex array of systems drainage, electrical conduits for lighting and monitoring systems, inspection walkways running inside the hollow steel box, girders, sensor mounting points for the structural health monitoring systems that would watch this bridge continuously for its entire operation, systems that would watch this bridge continuous the hollow steel box. The deck is not a road laid on top of a structure. The deck is part of the structure. It contributes to the overall stiffness of the bridge, works in conjunction with the cables to distribute load, and must perform all of these structural functions while simultaneously serving as a smooth, safe surface. Before a single public vehicle was permitted to cross the Duge Beipanjiang Bridge, the structure was subjected to a comprehensive load testing program. Convoys of heavy trucks, vehicles of known weight, positioned at precise locations along the deck, were used to apply controlled loads to the structure. Surveyors measured the deflection of the deck under load. Engineers compared the measured deflections against the predictions of the computer models. Accelerometers recorded the dynamic behavior of the bridge under moving loads. Strain gauges embedded in the structure confirmed that forces were being distributed as designed. Wind sensor recorded the aerodynamic response of the deck under natural wind loading. On the 29th of December 2016, the Duge Beipanjiang Bridge opened to traffic, and the 5-hour journey became roughly 1 hour. Most drivers who cross this bridge today see almost none of what makes it extraordinary. They see a road, a smooth, well-maintained, 4-lane expressway. They might glance over the edge and feel a brief, vertiginous awareness of the height, but they do not see what is beneath their wheels. They do not see the 720-meter main span of cable, stage structure, a web of individually tensioned high-strength steel cables, each one monitored continuously by sensors that transmit data to a control center in real time. They do not see the 2 towers, rising approximately 269 meters above the canyon rim, their internal concrete shells, housing inspection staircases, maintenance access routes, and the massive cable anchorage assemblies, where the forces of the entire bridge structure converge into 2 points of rock and steel. They do not see the foundations beneath those towers, sunk deep into the limestone of the canyon rim, engineered to carry not just the weight of the bridge, They do not see the structural health monitoring systems, the network of accelerometers, strain gauges, temperature sensors, and anemometers embedded throughout the structure, watching every vibration, every load cycle, every thermal expansion and contraction, transmitting that data continuously so that engineers can know, in real time, whether the bridge is behaving exactly as it should. They do not see the inspection walkways running inside the hollow steel deck boxes, walkways where maintenance teams crawl through the interior of the bridge. Inside the roadway, they are driving on to inspect welds. Check for corrosion, verify the integrity of every connection. They do not see the drainage systems, managing the water that falls on the deck, routing it away from the structural steel to prevent the corrosion that over time would silently destroy what took years to build. They do not see the fog, not anymore, because the bridge itself, by existing, has made the fog irrelevant. Before this bridge, fog in the canyon meant the road was impassable. Now the road is above the fog. The drivers are in clear air. The cloud is 400 meters below them, filling the canyon like water fills a bowl, and they are driving across the top of it on a road that should not exist, in a place where roads were never meant to be. That is what engineering does at its highest level. It does not simply solve problems. It changes the relationship between human beings and the landscape they inhabit. It takes a canyon that said no for 1,000,000 years and makes it say yes. It takes 5 hours and turns them into one. It takes isolation, the kind of isolation that shapes lives, limits economies, constrains possibility, and it dissolves it permanently. The Duge Beipanjiang Bridge is 1,341 meters long. It is 565.4 meters above the river. It opened on the 29th of December 2016. Those numbers are real. Those numbers are confirmed. But the number that matters most is not in any engineering specification. It is the hours returned to every driver who crosses it. It is the goods that can now be delivered. The patients who can reach hospitals, the students who can reach schools, the families who can visit each other without losing a day of their lives to a mountain road. Engineering, at its best, is not about structures. It is about what structures make possible. That is the hidden truth of the highest bridge on Earth. It is not made of cables and concrete. It is made of time. If this video added something to your day, a sense of scale, a sense of what human beings are capable of when they commit to solving a problem, then subscribe to the channel. Leave a comment telling us which mega project you want us to cover next. We read every single one, and we will see you in the next video.